All right, hey everybody. So let's do the second half of this by picking up and talking a little more about neutron stars and then moving on to black holes. Um, so remember, when you've got a high mass star, say a star that's between 8 and 20 solar masses, when that iron core has completely converted, when the core of the star has completely converted into iron, then it collapses under gravity. It converts into just a ball of neutrons that then collapses down even more. Meanwhile, the rest of the star is exploding as the supernova. And the other thing that we haven't talked about is that as that core shrinks down smaller and smaller and smaller, it's going to spin up faster and faster and faster. Kind of like the classic example is when you see an ice skater, right? When an ice skater is spinning in place and then pulls their arms tighter and tighter against their chest, and then they start spinning up faster and faster. It's all an example of Newton's first law, right? That an object in motion will stay in motion. Well, if an object in motion tends to stay in motion, then an object that's spinning tends to keep on spinning because it has the same rotational inertia. But in order to maintain the same rotational inertia, as it gets smaller and smaller and as the mass gets more compacted toward the center, it spins faster and faster and faster. Which, in the case of neutron stars, becomes extreme because when that star was a main sequence star, the core was probably spinning once a month. It's about what the core of the sun spins. That's about how fast the core of the sun spins, rotating once a month. But as you go from being this big iron core to collapsing down in a fraction of a second, collapsing down to being the size of a city, it goes from spinning once a month to spinning about 100 times a second. So these things are spinning very fast. And when that star was a main sequence star, it had a magnetic field. The star was generating a magnetic field. But again, in a fraction of a second, that core went from being a big ball of iron to whoosh, becoming this tiny ball of neutrons. And then as that core was collapsing down into the neutron star, that magnetic field got concentrated. The magnetic field got shrunk down too, and so it went from being a strong magnetic field to being an insanely strong magnetic field. Not because the magnetic field exactly got stronger, but because the force of it just got more compressed. It got more concentrated. It got more intense. And so what you've got, once you form your neutron star, what you've got is this very dense, very small object, like 10 kilometers in diameter. It has a strong magnetic field. What am I saying here? 10 to the 12 or 10 to the 15. That's a trillion to a quadrillion times stronger than the Earth's magnetic field. And spinning 100 times a second. Well, when you have a strong, fast-moving magnetic field, that magnetic field can exert really strong forces on charged particles. Essentially, what you've got is a natural particle accelerator. That neutron star. So you've got this neutron star. It's spinning very, very fast, and the north and south magnetic poles, as these magnetic poles are whipping around 100 times a second, those magnetic poles, the magnetic field, are able to grab onto the charged particles that are around it. And again, this neutron star just blew up, right? Or the neutron star just blew up the rest of the star. This neutron star is now surrounded by the supernova remnant. There's a lot of hot ionized charged particles around to be grabbed onto. So the magnetic field is able to grab onto the charged particles around it, and it starts accelerating those charged particles along the north and south magnetic poles. And so basically this star is now shooting out two beams of charged particles and light. Well, if you happen to be sitting, let's say, here, right? This neutron star now looks like a lighthouse, right? It's got two beams of light shooting away from it, one out the North Pole and one out the South Pole. And if the Earth is over here, let's say, if the Earth is here, then every time that beam is pointing at the Earth, we get a flash of light. And then the neutron star rotates away, and it rotates back and flashes us again, and again, and again, and again. Every time that neutron star spins, it rotates toward us, and we get a flash of light in the face, a pulse of light in the face. That's why these things are called pulsars. Because if you look at this neutron star, this is essentially what you're looking at here is a graph of brightness versus time. So that as time progresses, every time that neutron star points at us, you get a pulse of light in the face. Pulse, 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 pulse. Because again, these neutron stars are spinning many times per second, which means many times a second, at regular intervals, we here on Earth see pulse, 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 pulse. This is the telltale sign that you're looking at a rapidly rotating neutron star. Nothing in nature is this nice. Nothing in nature is this regular and repeating. In order for us to see, we see these flashes of light, you must be dealing with something very fast, very rapidly spinning, very strong, with no variation. And so, if you're looking at these neutron stars, well, typically what you'll see is something like this, where this is a picture of the Cas A supernova remnant. So this is a nebula created by the exploded supernova, and then at the center of that nebula, at the center of the supernova remnant, is the neutron star. And if you watch this if you can watch this with very rapid response, if you can watch it over the course of a few seconds, what you see is just the flashes. The flashes of light as this neutron star points its north pole at us, or maybe it's the south pole, hard to tell, but it points one of the magnetic poles at us once per rotation, which is multiple times per second. All right, let's get on to black holes. It's what you've been waiting for, isn't it? All right, well, in order for us to understand black holes, we need to get an idea about how gravity works from a different point of view. All right, so we need to talk about how our understanding of gravity changed about 100 years ago. Because we've been dealing with gravity all semester long, but most of the time we've been dealing with it in terms of Newton's idea about gravity, right? That gravity, according to Isaac Newton, gravity is this invisible force pulling massive objects together. About 100 years ago, Einstein comes along and says, well, that doesn't really make a lot of sense, right? How can there be some invisible force pulling things together? Like, why do stars and planets pull each other together even though they're not touching? How can things pull each other together over empty space? How does that work? How does gravity really work when you get down to the nuts and bolts? And when you start digging down that rabbit hole, you get very few satisfying answers. And so Einstein, about 100 years ago, starts digging in and starting to say, well, okay, but okay, for things like the sun, the earth, the moon, yeah, gravity works the way Newton says it does, but why? And in doing so, he actually figured out that gravity doesn't work the way Newton says it does. That gravity actually works by a completely different mechanism. So Einstein comes up with a completely different theory for how gravity works. Einstein calls this theory general relativity. So you've probably heard of Einstein's theory of relativity. Einstein's theory of relativity has two parts to it. There's special relativity and there's general relativity. General relativity is his theory of gravity. So that's what we're focusing on here. Einstein's theory of gravity, general relativity, really is a theory of space. It's a theory of space and time and what they're really made of. So we need to talk about dimensions for a second. All right? If you talk about something that has 0 dimension, okay, that's just a point in space. Something that has 1 dimension it's a line, it has length. If something has 2 dimensions, then it has length and width. If something has 3 dimensions, it has length and width and height, right? But then there's a 4th dimension, and that is time, right? Because for all of physics, going back to, Galileo at the latest, physics always treated space and time as being 2 different things. That we lived in a universe of 4 dimensions of space, right? Everything in our universe has like length, width, and height. But then, you could deal with how things move through time, but that's a separate thing, right? Time and space are 2 different things, right? That's the old idea. That's how Galileo and Newton treated it. Einstein says no. Einstein says you can't treat space and time as being different because when you move through space, you also move through time, right? If you throw a ball, let's say you take a ball and you throw it through space. As that ball travels through space, it's also traveling through time, right? That ball has to travel after 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. You can't travel through space without also traveling through time. You can't treat them as 2 separate things. That space and time are essentially the same stuff. And Einstein just calls it space-time. That the fundamental game board on which the game of physics is played, the chessboard on which the game of physics is played, the fundamental stuff of reality, the fundamental firmament of reality is this 4-dimensional space-time. And that when you travel through space, you're also traveling through time. So you might as well treat all 4 dimensions as being the same thing because basically they are. And then it gets even weirder. Because if, Einstein says, if you throw a ball and it travels in a straight line, well, that must be because the space-time that the ball is traveling through is flat. Much like if you have a flat table, right? If you have a flat table and you roll a ball across a table, that ball is going to roll in a straight line. But if the table is tilted, let's say the table is tilted so it's high on the right and low on the left, right? Then if you roll a ball, it's going to roll down to the left because the table's not flat. According to Newton, if you throw a ball and it travels in a straight line, that must be because it's just coasting on its own inertia. There must be no forces, right? Newton's first law of motion is an object in motion will stay in motion, or an object at rest will stay at rest, unless it's acted upon by no outside force. So that if you throw a ball, it's just going to go in a straight line when there's no forces acting on it. According to Einstein, if you throw a ball, that ball is moving through space. And so the shape of the space affects how the ball is going to move. That ball, if you throw a ball, that ball will only move in a straight line if the space-time that it's traveling through is flat. If it's curved, though, then if the space-time is curved, then things will take curved paths. Because, and this is where it gets even weirder, space-time is stretchy. Space-time is apparently flexible. like a rubber sheet. Um, and so if you zoom in, let's go back here real quick. According to Einstein, if you zoom in at the most fundamental scales of reality, when you look at space itself, space-time itself can move, it can stretch, it can flex. It is like a rubber sheet. It can bend. And so what Einstein said is, what we call gravity, this thing we call gravity, is actually just the bending of space-time. That gravity is not a force. Forget that old Newton idea. Einstein's theory of gravity is a completely different concept of what gravity is. So I need you, and Einstein is asking you, completely forget about Newton. Gravity's not a force. Einstein says that massive objects like the sun and the earth, because those objects have mass, they bend the space-time around them, and that because the space is curved, straight lines aren't straight anymore. Like this straight line isn't straight anymore. It's now a curved line. Curved, why do straight lines become curved? Straight lines become curved because the space they're moving through is curved. And so Einstein says this is a completely different idea about orbits, right? Because if the Earth, why does the Earth orbit the sun? Well, Earth wants to move forward. Earth wants to just coast through space, coasting on its own inertia. An object in motion wants to stay in motion. And so here's the Earth. The Earth has some speed, and it wants to coast. And it wants to coast in a straight line. But because the Earth is near the sun's mass curves the space-time around it, so that instead of coasting in a straight line, the Earth takes a curved path because the space that it's traveling through, as the Earth orbits around the sun, the space that the Earth is traveling through is curved by the sun's mass. And so instead of flying off in a straight line, the Earth is now orbiting around the sun because the Earth's path, the Earth's trajectory, is curved by curved space-time. According to Newton, you would say, oh yeah, there's a force between the Earth and the sun, and the sun is pulling on the Earth, and that's why the Earth orbits the sun. Einstein says, Einstein says the sun's mass curves space, and then because the Earth is moving through curved space, the Earth takes a curved trajectory. That what we call gravity is not a force, Einstein says. Gravity is just the geometry of space-time. If you're moving through flat space, you move in a straight line. If you move through curved space, you take a curved path. Einstein was living at the end of the 19th and the beginning of the 20th centuries. Einstein came up with this in 1915. The fastest thing in the world when Einstein was working on this was a train. A lot of Einstein, if you go and read Einstein's writing about relativity and stuff, it's all very quaint and old-timey because he's just talking about like, well, if you get on a train and if that train goes fast enough, airplanes were just being invented by the Wright brothers and stuff, right? No, but Einstein had never been on a plane before. A bicycle was the main way to get around for Einstein when Einstein was growing up, and a train was like the fastest thing you could imagine. And so Einstein says, hey, if you get on a train, if that train is traveling in a straight line, why doesn't that train just, if the Earth is curved, why doesn't that train just go right off the tracks and fly right out into space? Why doesn't the inertia, why doesn't the momentum of a locomotive just carry us right off the Earth and out into space? And Einstein says, well, it's because the Earth has mass. And because the Earth has mass, the Earth is curving space-time. So if you're on a train moving along the tracks, your body and the train itself is moving through curved space-time. Think about it like this. Think about this for a second. Your body is sitting there, right wherever you are right now. Your body is bathed in space-time. Your body, my body, we are all like swimming in an ocean of space-time. It's the space around your body and it's the space inside your body. It's the space in between your atoms. And because we're all standing on the Earth, the space that we are swimming through is stretched by the mass of the Earth. And since we are moving through curved space, if you try to walk in a straight line, you're not going to walk in a straight line, because if you could walk in a straight line, you would walk right off the Earth and out into space. If you try walking in a straight line, you're going to walk in a curved path along the surface of a curved planet. Because straight lines become curved lines in curved spacetime. That's why gravity, that's why Einstein's idea of gravity is totally different than Newton's. Right? According to Einstein, gravity is not a force. Gravity is just this name that we've given to the fact that space-time curves the way mass tells it to. That the mass of an object, like a star or a planet, the mass of an object curves the space-time around it, and then that curved space-time tells objects moving through that space how to move. That's why you and I are standing here on the surface of the Earth. Now, there's an interesting implication to Einstein's theory of gravity, which is, according to Isaac Newton, gravity is a force between two objects based on their mass. Well, light doesn't have any mass. So according to Isaac Newton, light shouldn't feel gravity. But according to Einstein, gravity is just the curvature of space-time. And so anything moving through curved space-time will take a curved path, including rays of light. So this was the big test. When Einstein came out with his theory of relativity in 1915, people said, wait. So you're saying not only is gravity not what we think it is, space and time aren't even what we think it is. Oh, and also light should feel gravity the way that people and planets and moons do? What? How could we test this? I mean, your math is all nice, Isaac, but not Isaac, sorry, Albert, right? Your math is all very nice, Albert, but is it true? Or are you just playing mathematical games with us? How can we test this? Well, the natural experiment is, let's see if light gets bent by gravity. Because if light doesn't feel gravity, then Newton must be right and Einstein must be wrong. But if light beams are curved by gravity, Einstein is right and Newton is wrong, and that'll be the smoking gun. That'll be the proof positive that Einstein's right and Newton is wrong. So that's what they did. In 1919, so this is a few years later, in 1919 there was a solar eclipse. And so a bunch of astronomers and physicists and reporters mounted a big expedition to the west coast of Africa, because that was going to be the prime place to see this solar eclipse. So why a solar eclipse? Because you want to see rays of light bending around the sun. Well, if you're seeing a ray of light near the sun, that's pretty hard to do during the daytime because the sun is way too bright. So it was a very dramatic. It made the front page of the New York Times. This was such a dramatic story about, a ship full of intrepid scientists traveling to the west coast of Africa to see a rare total solar eclipse, yada yada yada. Right, the newspapers loved it. The moon covers up the sun, and because the moon is blocking the sun, now you can see the stars behind the sun. which you normally can't do because it's daytime. And right in the middle of the solar eclipse, there was a bunch of telescopes, astronomers with telescopes taking pictures of the eclipse. You could see the stars behind the sun. So let's say here we are on the Earth. Here's a star over here behind the sun. And right during the eclipse, the photos that were taken showed that the star that in actuality is back here, that starlight was shining this way. It was bending around through the curved space-time of the sun, and it was shining on us here on the Earth. So that if you're on the Earth over here, the star looks like it's coming from back over here. The starlight looks like it's coming at us from over here. So we know, because we had good star charts, we know that this star should be over here, but actually we saw it over here. That's the appearance of the star, the position of the star was bent because it was traveling through the bent space-time curved by the mass of the sun. Not only was the path of those stars bending, but those rays of light were bending by exactly the amount that Einstein's equations predicted they should be. That was the smoking gun. That was the huge news. This is why it made the front page of the New York Times, is because this was the proof, the absolute direct evidence that says not only was Einstein right, but apparently our whole ideas about space, time, gravity, light, the fundamental ideas of reality are not what we have been classically trained to think they are, in ways that are not entirely intuitive for human experience, but there it is. That star should be here, and it's over here. A simple observation like that shows that, yeah, gravity isn't a force. It's just curved space. Now, why have we been talking about Newton's theory of gravity for this whole semester so far? And the answer is because it's mathematically much easier, right? If you can deal with, let's see, we were looking at that in the last lecture, most of the time, for most more normal things in the universe. Oh, where did I put that? I know it's on one of the, I know I put it on, there we go, right? We were looking at this in the last lecture, right? For most things in the universe, stars, main sequence stars, planets, moons, people, for most normal mundane stuff in the universe, Newton's theory of gravity works fine. You just have to take that small grain of salt and remember, well, Newton's theory isn't true, strictly speaking, but the math works out, and the math works out much easier than Einstein's equations do, so we'll use that. We'll use that if we can. It's when you get to really extreme gravity. It's where you start dealing with the gravity very close to main sequence stars. Or when you talk about white dwarfs, neutron stars, and black holes. When you start talking about the gravity very close to very dense objects, then gravity doesn't behave the way Newton says it should. You have to switch to Einstein's equations. To wit, this is how you get a black hole. Because oh, my brownies are done with the oven. I'll be back in just a second. Okay, I'm back. Just made you hungry, didn't I? All right. So, one of the implications of gravity is, how do you fight against gravity? How do you escape from the gravitational pull of a planet or a star? And the answer is, you just need to get going fast enough, right? All you need to do in order to leave the Earth is get on a rocket, and if you can go fast enough, then you can get away from the planet before the planet's gravity has a chance to slow you down and pull you back in. So that minimum speed, the minimum speed that you need to go in order to escape the gravitational pull of a planet, is what's called the escape speed. If you're going slower than the escape speed, you'll shoot up in the air and then fall back down. if you're going at or faster than the escape speed, then you will be able to escape that object's gravity and get out to infinity. So let's think about what that means on the surface of a star, let's say. Let's say you were standing on the surface of the sun, which, not a great idea, but let's just say. Right? If you're standing on the surface of the sun, you're very close to all of the mass of the sun, and so you got to be going pretty fast. But it's doable, right? If you get going really, really fast, you will get away from the sun before the sun's gravity has a chance to slow you down and pull you back in. Now, what if the sun were to start shrinking? What if the mass didn't change, but the sun was just getting smaller? Well, now you're getting closer to all of that mass. And if you're closer to all of that mass, then the space that you're sitting in, the space that your body is bathed in, is getting more curved. It's getting more stretched and more curved because you're closer to all of this mass. And if the space-time that you're sitting in is more curved, then you've got to get going even faster in order to escape the star's gravity. So then let's take that to the extreme, right? One of the ways, a lot, and we've been looking at these for a minute now, but one of the ways to sort of illustrate space-time and the curvature of space-time is with these sort of diagrams right here. Now, this is a little tricky and hard to understand because space-time is four-dimensional. It's got 3 dimensions of space and 1 dimension of time. But in order to draw them on a PowerPoint slide, or in order to draw them on paper or something, you kind of throw out one of the 4 dimensions. Let's just, ignore one of the 4 dimensions. And that way you can draw this diagram as having length, width, and then some depth. And then the depth here represents the curvature, right? The more steep, right, as you get closer and closer to the sun, that space-time is getting curved more and more steeply. If the space-time is steeper, that means the curvature is greater, and therefore the quote-unquote gravity is stronger. So, if you take the sun, and if you start collapsing it down into it where the mass doesn't change, but the mass is just getting denser and more concentrated, then near the surface of the sun, the space-time is getting more stretched. The space-time is steeper, and therefore you've got to be going even faster to escape the gravitational pull of that star. But only near the surface, right? Out here, there's a reason why I said, for things like the Earth, we don't need Einstein's theory. We can use Newton's theory because out here, the space, if let's say the Earth is here, the curvature of the Earth's space-time is, fairly flat. It's not totally flat, but it's not terribly curved. And that means, because the gravity isn't too extreme, mathematically speaking, gravity works the same as it does in Newton's equations. It's only when you're near the surface, here, and especially here, where the gravity becomes so extreme, the stretching of space-time becomes so extreme, you can't use Newton's theory anymore, you've got to use Einstein's theory. But if we take this star and start shrinking it down smaller and smaller and smaller, the space-time near the surface of that star gets more and more and more stretched until that star becomes microscopically small. And if you could take the mass of a star and shrink it down, compress it down into take all of that mass and compress it down into something microscopically small, then that object would become so dense that near the surface, the space-time becomes so extremely stretched that the escape speed becomes faster than the speed of light. And nothing can travel faster than the speed of light. Nothing. Which means if you're too close to that object, you can't escape. Right? The speed that would be required to get out of the black hole is faster than the speed of light, and nothing can travel at faster than the speed of light, so you're trapped. That's why it's called a black hole, because nothing can get out of it. Nothing can escape its gravity. Nothing can escape space-time that is curved that strongly, not even light. Right? And that's the misconception. The idea is, oh, a black hole is like just a vacuum sucking up everything near it. No, 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 no. A black hole is perfectly safe if you're far enough away, right? Because whether you're talking about a star like the sun, or a white dwarf, or a black hole, if you're nice and all the way out here, everything's fine, right? If you're far enough away, then the curvature of space-time hasn't really changed much, and therefore the gravity that you feel is the same. The extremity only becomes near the surface. As that black hole gets more and more and more compact, smaller and smaller and smaller, the gravity near the black hole gets stronger and stronger and stronger until nothing that has mass, no particles, or no light can escape. The point of no return is what's called the Schwarzschild radius. So as long as you're outside of that Schwarzschild radius, then the escape speed is not faster than the speed of light, and you're safe. But at some point you get too close to the black hole, the curvature becomes too steep, and the escape speed becomes faster than the speed of light, and you're trapped. And light is trapped, and everything is trapped. So the point of no return, the place where you're too close to the black hole and you can't get out again, is what's called the Schwarzschild radius. And the Schwarzschild radius is essentially 3 kilometers per solar mass. So if you could take the sun, somehow, if you could take the sun and compact it down into something smaller than 3 kilometers, it would be a black hole. Now, realistically, that's not going to happen. The sun won't turn into a black hole. But if you could somehow magically shrink the sun down to that size, it would become a black hole. The size of the Schwarzschild radius only depends on mass. The bigger something is, the bigger the Schwarzschild radius is. So the sun is like, 9 kilometers. Something that's the mass of the Earth has a Schwarzschild radius of 3 kilometers, 9 millimeters. The moon has a Schwarzschild radius of 0.1 millimeters. So basically, if somehow you could take the mass of the moon and squeeze it down to be the size of a grain of sand, it would become a very small black hole. Realistically, that's not going to happen. Realistically, this is why only the highest of high mass objects die and become black holes. Because it takes several solar masses in order to have gravity be so strong that gravity will pull all of that mass into an object smaller than the Schwarzschild radius so that it becomes a black hole. The boundary of the Schwarzschild radius, the boundary between the inside of the black hole where you can't escape from and the outside of the universe where everything's fine, is what's called the event horizon. So basically, the event horizon is the boundary of the black hole, right? The event horizon is a bubble. It's a sphere whose radius is the Schwarzschild radius. And as long as you stay outside the event horizon, if you're in a spaceship orbiting around a black hole, as long as you're outside the event horizon, you can still escape. You got to go very fast to escape, but you can do it. It's not impossible. But as soon as you go inside the event horizon, you can't get out again. Because in order to get out, you'd have to go faster than the speed of light, and nothing can travel that fast. We can't see the inside of a black hole, right? You can't just point your telescope and see what a black hole is like, because no light is getting out from the black hole for that light to arrive at our telescopes. The only way we can see a black hole is by looking around the black hole, by looking at the environment right outside the event horizon. We think, the the math that we get from Einstein and then a lot of work on gravity that's been done over the last 100 years suggests that inside the event horizon, um, all of that mass, the gravity is so strong, the space time is so curved that all of the mass has been squeezed down into a single point in space, what's called the black hole's singularity. So when you talk about a black hole, like what is it? Well, what is a black hole? Well, a black hole, on the face of it, is the singularity. All of the mass, many solar masses, have been squeezed down into a single point in space, a single particle. But the singularity is a single particle with 10 times the mass of the sun, 20 times the mass of the sun. Inside, near the singularity, that's where the space-time is so stretched that light, nothing can escape. It's when you get out to the event horizon that the escape speed is insanely fast, but not impossibly fast. And so we can see, if you point your telescope at a black hole, you can't see inside the event horizon. No light escapes from there for us to observe. You can only see what's going on right outside the event horizon, so that if something's going on outside the event horizon, like let's say there's a blob of gas falling in toward the black hole, that we can catch. And so if you can see the environment around the black hole, if you can see the environment right outside the event horizon, then you can try to make some inferences about what's going on inside. Which is a problem. Because we're only making inferences. When you start drawing conclusions about black holes, you're trying to make a conclusion based on the evidence you have. But the evidence that you have is not of the black hole itself, it's just from right around the black hole. What's going on inside the black hole? What's going on inside the event horizon? We don't know. We can't get any information from via light from inside there. So this is where modern physics becomes very cutting edge. There are a lot of people working today to come up with new theories, better theories of gravity. Right? Einstein's theory of gravity is probably not the end. It's probably not the theory of gravity that we'll have in another 100 years. Because there are lots of questions about what is it like as you get really close to a black hole? What is it like at the singularity where the mass is huge and the curvature is strong and the density is, I don't know, infinite, right? If you take the mass of a star and squeeze it down to having zero volume, is the density insanely high or is it infinitely high? Is the size small or is it infinitesimally small? These are questions you can't just point your telescope and see. And different ways of trying to figure out how gravity works come up with slightly different results. So there are people trying to make the next new theory of gravity today. And the reason why we need a new theory of gravity is not for all the normal boring stuff like, us walking around here on Earth. Newton and Einstein work just fine. But we want to know how gravity works in really extreme environments, like at the center of a black hole, or during the Big Bang. When the universe, right after the universe popped into existence, at a fraction of a second after the Big Bang, the universe was very hot, very small, very dense. Space-time would have been curved very strongly, sort of like what's happening near a black hole. So this isn't a, when people talk about new theories of gravity and why do we work on them, why are they worth working on, it's not just to figure out about these peculiar black holes, although they're pretty awesome and that's a good enough reason if you ask me. The reason why we want to do that is because this has implications for the whole universe. When the whole universe, right at the very beginning, the universe was a lot like what it's like inside of a black hole. And so if we can figure out what black holes are like, then we can figure out what the whole universe, what like capital E, everything in existence was like at the very beginning of time. And so when you've got questions about why is the universe like this? Why are we here? Why are there stars and planets and galaxies and people and reality television and used car dealerships? If you want to know why is the universe that we see the way that we see it, a lot of those answers go all the way back to the Big Bang. And because the universe was like this at the Big Bang, that explains why the universe is like this 14 billion years later. But when you try to figure out why was the universe like that right after the Big Bang, that's where you also, as you get closer and closer and closer to the Big Bang, as you get trying to answer what was the universe like sooner and sooner after the Big Bang, it's kind of a lot like asking what space and time and heat and temperature and matter and energy are like as you get closer and closer to the center of a black hole. If we can solve one problem, maybe we can solve the other one, and then we'll have a better understanding of what the whole universe is doing. So these are very big questions about very small objects, is what I'm saying. All right. This begets a natural question, which is to say, are these things real? Right? If you can't just point your telescope and say, yep, there's a black hole. I know there's a black hole. I can see it, because you can't see it. How do we know that they're real at all? Are these black holes just some sort of like mathematical toy that come out of Einstein's math, but they're not real? Or are they real things that exist in the universe? Well, I'll just say yes. Okay, spoiler alert, yes, the answer is yes. But why pretend there's any suspense? How do we know, though? How do we know that black holes are real? Well, the first one that was ever discovered, for sure, was what's called Cygnus X1. So Cygnus X1 is this bright X-ray source in the constellation Cygnus, hence the name. And Cygnus X1, when you point a visible light telescope, you see a blue supergiant. You're like, all right, it's a blue supergiant. But then when you look at that object in the X-rays, it's giving off way more X-rays than it should be doing. You're like, wait, I mean, it's a blue star. It's a hot star, but not nearly hot enough to be glowing with a lot of X-rays like it is. And then you study Cygnus X1 some more, and it turns out that it's a binary system. That Cygnus X1 is that the blue supergiant is a star orbiting around a binary companion every 6 days. That the blue supergiant and its binary companion are orbiting each other every 6 days, which is pretty darn fast. But there's way too much gravity there. This blue supergiant has a mass of 30 to 40 solar masses. The companion, though, must have about 15 solar masses. And when you point your telescope at that star, there's nothing there, right? All you see is the blue supergiant. That blue supergiant should be orbiting around something. What is it orbiting around? Whatever that thing is, it has 15 solar masses. It is exerting 15 solar masses worth of gravity, and it's emitting no light. We know it can't be a neutron star. A neutron star can't be more than 3 solar masses. We know it can't be a white dwarf. A white dwarf can't be more than 1.4 solar masses. So whatever this thing is, it's got 15 solar masses worth of mass, and it emits no light. It has to be a black hole. Here's a sort of a painting of what we think this thing actually looks like if you could get up real close. Here's the blue supergiant, and there's some mass transfer siphoning off the star, falling into an accretion disk around the black hole, and then as that gas is spiraling in toward the black hole, this gas is heating up to a few million Kelvin, and it's this gas, it's this superheated gas in the accretion disk that's the X-ray source. That's where all this excess X-ray radiation is that you can see in your X-ray telescopes. These two stars the star and the black hole are orbiting around each other, and yet, you see there's the star, there's an accretion disk, Where's that 15 solar masses? You don't see it. It must be a black hole. What else could it be? It turns out Cygnus X1 was discovered in, I want to say, the 70s. But it turns out there are two types of black holes. That there are the small kind and the big kind, which seems ridiculous to say because, like, they're black holes. They're all compacted down into the singularity. But what do I mean? So what we were talking about here, Cygnus X1 is what you call a stellar mass black hole. It's got a mass of, 15 solar masses. Stellar mass black holes have masses that are a few dozen solar masses. 15, 20, 30, 50 solar masses. When you look toward the center of our galaxy, there's something at the center of our galaxy. This object is what's called Sagittarius A star. And there's something there. The problem is you can't really look, it's very hard to point your telescope toward the center of the galaxy because in the visible spectrum there's a bunch of stars and gas in the way. But if you look in the infrared, if you look through an infrared telescope, you can see through a lot of the gas and the dust, and you can see all the way toward the center of the galaxy. Here's what the center of the galaxy looks like in an infrared telescope. Each of those blobs is a star. So here we're looking at the very center of the galaxy. Here are a bunch of stars near the center of the galaxy. And then if you watch, so this picture was taken in the middle of 1995, hence the tag there. If you watch the center of the galaxy for a few years, here's what you see. All of these stars are moving around something. They're orbiting. So in between 1995 and 2010, all of these stars are moving around. This one in particular, right? But these stars are orbiting around something. Whatever they're orbiting around, it looks like it's right there, that star in the middle. And yet that object there in the middle is emitting no light. None. Right? What's giving off light? These stars are giving off light. We know what's giving off light. We can see them in the telescopes. These are real pictures of the infrared emission, the infrared light coming off those stars. At the center of our galaxy is an object. It has a strong enough gravity that it's pulling all of these stars in orbit around it. When you use Kepler's third law, just like you did for the binary stars homework, in the binary stars homework, you use Newton's version of Kepler's third law to predict the mass of the binary stars, right? You can do the exact same trick here and say, what is the mass of that object pulling this star into orbit around it? It turns out Sagittarius A star has a mass of 4 million solar masses. Whatever's there at the center of the galaxy has 4 million times the mass of the sun, and it emits no light. What could possibly have that much mass and yet be giving off no light? It has to be a black hole. Nothing else that we can think of, nothing else that we know of or can imagine can have that much mass and yet be so dim as to give off no light. It has to be a black hole. And yet this is not a stellar mass black hole. This is not a black hole that has 15, 20 solar masses. This has 4 million solar masses. And so astrophysics has taken to calling these things supermassive black holes. That's the name that we've given them. I'm not just making that up. They're called supermassive black holes because these are not one star dying and becoming a black hole. This is a completely different beast with millions of solar masses. It turns out this is not uncommon. It turns out we've discovered supermassive black holes sitting at the center of lots of galaxies. They might be there at the center of most galaxies. But we're going to start talking about galaxies pretty soon here. So we'll talk more about this later. But it turns out that, yes, at the center of our galaxy, and maybe even at the center of most galaxies, there is a supermassive black hole with millions, or in a few cases, a few billion solar masses all collapse down into an infinitesimal singularity, and yet no light can escape the black hole, so you can't see it. You can't see the black hole itself, but you can see, we know that it's there. We know that this supermassive black hole is there because we can see the influence that its gravity is having on the environment around it. So yes, black holes are real. You can't see the black hole, but you can see the effect that it has on stars and gas right outside the event horizon. That's how we know these things really exist. It took a long time. Einstein came out with general relativity in 1915, and it wasn't until the mid-70s that we saw Cygnus X1, which was the first object compelling enough to say, oh, no, these things are real. For 50, 60 years, people were sort of debating, like, well, the math works out nicely, but, are these black holes real, or do they actually exist in nature? Or is this just some mathematical fluke that never actually happens? Nope, turns out they happen. Turns out they happen during the deaths of stars over 20 solar masses, and it turns out they happen at the center of most galaxies. What do they look like in other galaxies? We'll talk about that soon. Okay. We've been okay. I just said this. Okay, so Sagittarius A star has a mass of 4 million solar masses, but it has a size of only about 17 light hours. What's 17 light hours, meaning a distance that it takes light 17 hours to cross it? It's about the size of the solar system. Right? 17 light hours is about the size of our solar system. So the event horizon, or the short shield radius of Sagittarius A star, is about the size of our solar system. And yet it has 14 million times the mass of the sun in there. It's supermassive, yeah. Okay, so we've been spending the last few lectures talking about the deaths of stars. But we've been neglecting to talk about how stars are born. And there's a reason for that. And that is because how stars die influences how the next generation of stars are born. So we're going to loop back and finish up the life cycle of stars. We've talked about how stars live, we've talked about how they die, we talked about what happens after they die. Now we're going to finish the story by going back and saying, well, now how are stars born after all? And after we talk about after we will have talked about the full life cycle of stars from birth to death, then we can zoom out and say, all right, well, what effect does this have on the entire galaxy? And then once we've talked about our galaxy, we're going to talk about, well, what about all the other galaxies in the universe? And so for the rest of the semester, we're going to be spending time zooming out, and then zooming out some more, and zooming out some more, looking at our galaxy, and then other galaxies, and then whole clusters of galaxies, and then the entire universe. Until, at the very end of the semester, the last thing to talk about is everything. Capital E, everything in existence. But the only reason why we understand any of that is if we understand the births and deaths of stars. So, we're going to finish up this next time, and then we'll start zooming out to look at the whole rest of existence to wrap up the semester. All right. So be well, everyone. Take care. See you soon.